Of these do we want to start with? I don't have a lot of time because I do have a 6 o'clock. In fact, I'm back to back to back to back tonight. So
I understand.
we'll go as far as we can. So you tell me how to prioritize. Which of these documents should I open first?
Let's see. One sec. Let me look at them.
Number 7.
Start at 42. All right, so that's, which one is that? That's the bottom left.
All right.
Let's try that one.
So are you on to?
So the goal today is.
Go ahead.
This is more a review for the test. So I just, I kind of want to just like sit back and listen to you explain these, because I just need to know that I'm prepared. So this is more like affirmation that I know things.
Okay.
But yeah, 42 is up in the air.
Newton came up with a very interesting method for calculating the zeros. I mean, remember that back then he didn't have any calculator that he could use.
Right.
So he came up with this process that is an iterative process where you guess a solution and then you improve upon it, and each improvement gets closer and closer to the solution. And his basic formula is that the second guess, which is x to the n plus 1, is equal to the first guess, x sub n, minus the function evaluated at x sub n divided by the derivative evaluated at x sub n. This ends up being an unbelievably accurate way to figure out the zeros. Notice that if you did not have a calculator, this would be an incredibly difficult problem. In other words, you have a trig function. If I move this to the other side, you have a trig function equal to a polynomial expression. Okay, so we do not have an easy way of finding these zeros. If I guess based algebraically, well, x equals 0 is going to produce 2 minus square root of 2 equals 0. So that's not particularly accurate, but it'll get the job done. You merely have to be close. Okay?
Okay.
Furthermore, this method does not always work. It only works on certain functions. On some functions, with each iteration, you don't get any closer to the true solution. So here's what I'm going to do. I'm going to guess x equals 0 as a solution, even though I know that's not right. It's still better than x equal 1. It's closer. So that's my first solution. Okay?
Okay.
Now, my second guess is going to be x sub n plus 1. Well, let's figure out what the second guess is going to be. Well, what is that divided by that? Well, it's f of 0, that's x sub n, my first guess. Let me label that, x sub n, divided by f prime of 0. This is going to give me my second guess, And let's figure out what f prime is. If this is f of x, what's f prime of x? It's the derivative of that part.
That would be 2 sine x.
Well, first of all, it's negative. Derivative of
Or negative
sine is
sine.
sine. So it's negative 2 sine x. Now let's make sure we don't draw a negative sign. And let's write that 1 plus x to the 1/2. So,
Right, so 1/2 times the quantity of 1 plus x times 1.
to the negative 1/2.
Or to the negative 1/2 plus
Times 1. In other words, you do have to apply the chain rule. Okay?
Yeah.
So now what is, let's figure out what f of 0 is and f prime of 0. So our second guess is going to be f of 0. What do you get when I plug in 0 there?
So you get 2 times 0 minus 1.
First of all, cosine of 0 is 1.
Oh, 1. Okay.
So that's 2 minus 1.
2 minus 1.
Okay. Yeah, and in fact, I'm confusing you because I didn't figure it out correctly the first time. Oh, Jesus, I didn't mean to do that. Hopefully I can do that. That's okay. Even though 0 is not a particularly great first guess, it works. Okay, so now I have 0 minus, and that was 1 in the numerator. And what is f prime of 0 equal to?
So that would be, what?
Now that's going to be 0. Sine of 0 is 0.
Right. Okay, I was getting those two confused again.
So it's going to be minus 1/2 times 1 to the minus 1/2, which is just 1. So f prime of 0 is going to be minus 1/2. Okay? And all of that is equal to a positive 2.
Yeah.
With me?
Yes.
Okay. So what this is telling me is that 2 is a better guess than 0. So now I go back into this function right here. Let's put red around it. And I'm going to come up with the next guess. Okay.
So how long would this go for?
Not very long. You'd be amazed. After 2 or 3 iterations, you've got a correct answer, sometimes to 6 decimal places. This is an amazingly accurate method. Let's at least do one more iteration so you know what we're looking at here. So my next guess, n plus 1, doesn't matter whether it's the 2nd, 3rd, or 15th iteration, it's the next one. So my next guess, I'm going to leave it called x of n plus 1, equals my last guess, which at this point is 2, minus f of 2 divided by f prime of 2. Well, now we got to go back up into the, here, let me open this up a little bit. Oh, good. So f of 2, wow, 2 cosine of 2. I guess you need a calculator to do that. You have your calculator with you?
I can get it, yes.
Yeah, go ahead and get it quickly if you could.
All right.
Make sure it's in radian mode.
All right, it is. So I got negative.
Everything in calculus needs to be in radian mode.
Right, I've never changed it from that.
None of calculus equations regarding derivatives and integrals of trig functions are correct unless you're in radian mode. Okay?
Right.
Or unless you're in radians. So f of 2 is 2 cosine of 2 minus the square root of 3. Can you give me a number on that?
Yes, that comes out to negative 2.564344.
Negative 2.564344. We got to be careful here. We don't want too much round-off error. I would say go out to 7 decimal places. What's the 7th decimal place?
A 5.
And what is f prime of 2, which is equal to minus 2 sine of 2 minus 1/2 of 1 plus 2 to the negative 1/2. And just to be clear, that's minus 2 sine of 2 minus 1 over 2 times the square root of 3. So what is that number?
It comes out to negative 2.10727.
And again, do you see what I mean by round-off error? In other words...
Well, but after... So I rounded up because it goes...
Well...
0.107269988.
They asked for the final answer to 6 decimal places. So if we round everything off to 6 decimal places, we're going to be in for some round-off error in our final answer. So what we usually do is that at every intermediate step, I take it to 7 or even 8 decimal places.
Even if it rounds up from there, though?
Yeah, and then I wait till I get a final answer that I can round off to 6 decimal places.
Okay.
Okay. So, I don't know. What's the rest of this? 1072 what?
10726998.
All right. That's good enough, I think. So now we need to do f of 2 divided by f prime of 2. So what's that number divided by that number?
Okay, one second. $1.216936.
1.216936. So that's that ratio, but notice that our next guess is 2 minus that ratio. So it's 2 minus that. So our latest x, we'll call this, our first guess was guess 1. So we'll call this our second guess.
All right.
Okay.
So that.
And can you do that real quick on your calculator just so I can write a number down?
Yeah, that'd be 783096.
All right. Now, that could be a pretty good guess. I don't know. I'm going to have to put this into Wolfram Alpha to see what the actual zero is. But let's do one more iteration. I mean, unfortunately, these problems are pretty time-consuming, but I want to make sure you understand it. So my first guess was 0. And my second guess was 2. This is actually my third guess, x sub 3. So we should be getting relatively close. But if I wanted to do one more iteration, then I would say, okay, x sub 4 is equal to x sub 3 minus the original function evaluated at x sub 3 divided by the first derivative of the function evaluated at that. And I can virtually guarantee you that x sub 4 will be probably within a thousandth or a 10,000th, actually 100,000th of the actual answer.
Wow.
This is an amazingly accurate method. How Newton came up with it, I'm not sure. They go through the mathematics here. It's pretty interesting, but and quite valuable. In other words, we would have had no way of doing this any time except in the last 50 years. I don't know, you could do it by trial and error. You could plot a bunch of points and see if you could estimate where the zeros are. Let me, at this point, plug this into Wolfram Alpha, and we'll see where the actual zero is. Not sure that's the best use of our time at the moment, but shouldn't take me too long to get this in there. What was it? It was 2 cosine x minus square root of 1 plus x. Is that right?
I just have written down the work here. Or
here, let me just double check that. Windows 10. Let's see, it was 2 cosine x minus 1 plus x, the square root of 1 plus x. Well, is that what I put in there? Yeah, it is. Okay. 2 cosine x minus 1 plus x to the 1/2. Notice where the zero actually is. 0.82836. So we're honing in on it. In other words, at our third guess, we're at 0.783096. Now, if we do the calculation for our fourth approximation, I shouldn't say guess anymore. The only one that was a real guess was the first one. But the way they're going to have the way they're going to tell you to suggest that you do this is you look at the graph and estimate a first guess. Well, in other words, if I had the graph and I didn't know what that precise zero was, my first guess might be 1, right? That's pretty close. Okay, so if I were to go back and do this again, my first guess wouldn't be 0, it would be 1. The closer your first guess is to the true zero, then the fewer iterations it's going to take you to get really, really close to the true zero. My first guess was bad enough that even after 3 iterations, we're not that close to the answer. The answer is 0.8 something, and we're at 0.78, somewhat close. But I guarantee you x sub 4 is going to be a lot closer to the true answer. If we wanted to go through the math. Okay? And we're not that far off. We're only 0.04 off. So we're pretty close, actually, given that we had a very wild first guess that wasn't very good. After just 2 steps, we're within 4% of the actual answer.
Okie dokie.
All right, we got only 7 minutes left. Is there one other?
All right, let's squeeze in one more. Can we do 40? That should be.
I see something 17 here.
That should be the middle of the. Or
which one do you want me?
Middle of the right side.
Middle right?
Number 40. Yeah, that one.
Okay. Yeah. All right. All right. I knew you were going to ask questions about this. This is, to me, this was always a difficult part, and worse yet, very few people get to this part. Your school is a little unusual, although I don't think this is going to be that hard. Let's see. Obviously, we need to come up with some differentials, right?
Yes.
So if I said, let's differentiate this and come up with what dy dx is. And then once I come up with it, I'm going to multiply both sides by dx, and my dy will be on the left all by itself, and my dx will be on the right along with whatever the derivative is. So let's differentiate that function real quick.
All right,
Using
so
the product rule.
let's see here. It would be 2x plus.
Hold on.
Mine.
It's always the derivative of that times that.
Oh, right, times. Sorry.
Plus the reverse. In other words, plus x squared times the derivative of e to the minus x. What's the derivative of e to the minus x?
E to the minus x.
Times negative 1.
Plus, or times negative 1, yeah.
In other words, you have to apply the chain rule for that part. Okay, so I can basically take this plus and that minus and turn it into a minus. The sooner you do that, the better, because it eliminates thinking that subtraction is going on there. So now I got dy equals this whole thing times dx. With me?
Yeah.
Even though these differentials are not fractions, most of the time you can treat them like they are fractions. In other words, to come up with this differential equation. Now, find dy, we just did, and evaluate dy for x equal 1 and dx equal 0.01. So
then you just plug those in and solve.
So they're basically saying evaluate, well, I can't really write it in the conventional manner, but yeah, dy is going to be 2 times, they said when x is 1, and dx is 0.01. Well, all of that produces a number, and that's what dy is.
Okay.
And you can get that out of your calculator. That's relatively simple. That's 2 over e minus 0.01 over e.
All right, those are simple enough. That's
1.99 divided by e.
All right. And can you tell me what the e approximation is, by the way?
2.71.
2.71.
Although your calculator has a key for it.
Right. I'm just worried that it'll be on a non-calculator part of the test.
Okay. Okay. Yeah, you want to know that I only know it to the 100th digit. I don't know what the next digit after 2. It's an irrational number. In other words, it goes on to infinity. But
yeah.
All right. Is there any other questions I can answer for you tonight, Matthew?
Those were the two I really wanted to touch on. I can do the other ones. They're just more review stuff.
Yeah. I do have your book. And it actually is helpful to me when you schedule a session if you put down what the material to be covered, not specifically. Like last time you said modeling and optimization. That's fine. That's
like in the notes?
Yeah, that's all I need. That tells me what chapter you're in and what subchapter you're in. and
Okay.
and then I can review it a little bit. But so you have not got to related rates yet?
I think we have. I think it's probably just under.
Related rates is a huge part of differential calculus. I would expect you're liable to have a number of questions on related rates.
Was that, what chapter is that in?
The one you're in right now.
Then yes, I think we do.
At the very end of it. It's right after Newton's method and the linearization stuff.
Well, we barely touched on Newton's method, so no, I don't think we did related rates yet.
You might not be there yet.
Yeah, we haven't.
Related rates are probably the hardest thing that you're going to come across up until now.
That's probably why he's saving it.
Well, I can help you with it a lot. It took me a long time to really get related rates, but I feel like I really understand them now. So feel free to contact me, and I'll help you with them when you get to them.
Okay.
There are some classic problems that will help you understand related rates.
Alrighty.
All right, Matthew. Have a good evening. I will talk to you next time.
Actually, and I think I'm meeting with you tomorrow at 11, or just online.
Hold on a minute. Let me bring up my calendar. Make sure I don't have that on here.
You don't?
No. December 13th? Did you schedule it online?
I did.
Today?
Oh, good thing we checked. Yeah, let's.
Yeah, let me. I didn't get a text message or and then it always shows up on this schedule. So you want me
I did do it on my phone.
You want to do an online session at 11 tomorrow? Is that right?
Yes, if we can.
Let me put it in there right now. For a half hour?
Yeah, just a half hour.
All right. Ah. Hold on. Put the wrong Matthew in there.
Actually, let me check something real quick, David.
Okay. Whether
Sorry.
the time works for you or not.
Yeah, let me just double
I got
check.
the whole morning, so if a different time works better, let me know. No, it didn't go in for next week either. I thought maybe you accidentally did it in the following week. But
You know, I don't even think that's. We probably don't even have to do that because I don't know what my schedule looks like tomorrow completely.
okay. Well, if you figure out your schedule and you need a session, let me know.
Okay, I'll text you. It's good to know you're open then. But.
Yeah, or better yet, just go in there and do it. Or are you doing these, or is your mom doing, when you schedule one, is that you doing it?
Yeah, I'm just doing them.
Okay, so you know how to schedule.
Yeah.
If a time, you only need like an hour's notice to get on here. So if you know at 9 a.m. tomorrow that you want to do an 11, you can go online and schedule it. And I don't think anybody else will take up that time. My mornings are fairly available. All right, Matthew, I got to run. I'll talk to you next time.
All right, thanks so much.
Bye-bye.